Hello and welcome to Scratch Chemistry. In this video we are going to discuss about the most peculiar organic compound, that is phenol. Okay, so in this chapter we will cover the structure, physical properties, chemical properties and methods of preparation and some name reaction, important name reaction related to phenol. So let us get started from structure. First of all, it's structure of phenol. All of you know the structure of phenol very well. So structure of phenol is what? This is an aromatic ring benzene, okay, attached to one functional group OH. This overall is no structure known as phenol, okay, OL for OH functional group, okay. So this is phenol, and one thing you marked, the functional group attached to the carbon atom is known as ipso carbon. This is ipso carbon, okay, and the nearest carbon, this carbon is known as ortho carbon, and this carbon is known as meta carbon, and this carbon number 4 is known as para carbon, okay. You can numbering it as 1, 2, 3 and 4, okay. 1 position ipso, 2 position ortho, 3 position meta and 4 position para, okay. This is the structure of phenol. So now coming to second, this is first property, second is physical properties. We will study the physical properties of phenol. Physical properties. So what are the physical properties of phenol in its nature, behavior, all the things? So first, physically, number 1 I point right. It is a colorless liquid or solid. What? It is a colorless, in short I am writing colorless liquid or solid. In pure form of phenol is solid, you can find. And second point is, right, in physical properties, second point is it is highly toxic. What? Highly toxic. So while you are using phenol in the laboratory, be careful. Third point is it has high boiling point. High, in short, high boiling point, BP. High boiling point. Why it has high boiling point? First of all, boiling point means the temperature, normal the temperature or heat required to boil any liquid, boiling point, okay. So high boiling point, the reason, because the reason here marked intermolecular hydrogen bonding. What the reason? Intermolecular hydrogen bonding. I have already discussed in the previous class intermolecular hydrogen bonding. So what is intermolecular hydrogen bonding? If one phenol molecule is at center and it is surrounded by the number of phenol molecule, okay, then there is a hydrogen bonding between each other or among each other. That is known as intermolecular hydrogen bonding. I am drawing the intermolecular hydrogen bonding structure. Let us suppose phenol, this is structure of phenol, one phenol group is here, okay, and at the surrounding there are different phenol groups, okay, molecules, okay, everywhere there is phenol, OH, okay, OH. So hydrogen intermolecular, particular inter, not intra, intermolecular hydrogen bonding. So electronegative element is oxygen attached to hydrogen. Here oxygen attached to hydrogen. Here oxygen, this hydrogen, let us suppose this side attached to this side, and this oxygen attached to this hydrogen. In this way there is a huge large structure or compact stable structure of phenol molecules forms. That is why we need more heat or more temperature to boil the phenol compound. That is why it has high boiling point, okay, because reason intermolecular hydrogen bonding. This is the third property. Then what is the fourth number property? Right here, number 4, it has high soluble. It is normal cell, not high soluble. It is soluble in water. Solubility, this is solubility property. It is soluble in water. Why it is soluble in water? Same reason, intermolecular hydrogen bonding, okay. In water, similarly, if suppose there is phenol and surrounded by water molecule OHH, okay, here the oxygen lone pair binds with hydrogen, also this hydrogen can bind to this oxygen of phenol. Okay, in this way there is also formation of intermolecular hydrogen bonding. That is why the phenol molecule is soluble in water. Okay, solubility. So in solubility I have a question for you. So between ortho nitrophenol and para nitrophenol. Okay, between ortho nitrophenol and para nitrophenol. In ortho nitrophenol, one nitro group is attached to the phenol ring, and in para nitrophenol, one nitro group attached to the para group, para carbon. Okay, so between ortho and para nitrophenol, which is more soluble? Which is more soluble in water? Okay, practice yourself, write in the comment box. This is a question for you. So another thing I missed here, in boiling point, if you compare the boiling point of cyclohexanol and phenol, both have almost same molecular weight, means cyclohexanol, okay, non-aromatic structure. This is the structure of cyclohexanol, and phenol is aromatic. Okay, and phenol both have almost similar molecular weight. Cyclohexanol molecular weight is 102 and phenol molecular weight is 94. But if you see compare the boiling point, if you compare the boiling point, you will find the phenol's boiling point is 185 degrees Celsius, where the boiling point of cyclohexanol is what? 155 degrees Celsius. Okay, 185 here phenol, because reason phenol is high, although they have similar molecular weight, but they have huge difference in their boiling point. Reason in phenol, because in phenol there is intermolecular hydrogen bonding. Okay, so another question. Okay, if you compare the boiling point of ortho nitrophenol, para nitrophenol and meta nitrophenol, so what are the differences? Ortho nitrophenol, meta nitrophenol and para nitrophenol. So all the structure you know, in ortho position nitro group, in meta position nitro group, in para position nitro group to phenol ring. So what is the boiling point? The boiling point of ortho nitrophenol is 215 degrees Celsius, and meta nitrophenol is boiling point 230 degrees Celsius, and of para nitrophenol boiling point is 245 degrees Celsius. So what is the order among ortho, meta and para nitrophenol? So down the group increases, means para nitrophenol have greater boiling point than meta nitrophenol, then ortho nitrophenol. Okay, so this is the order. What is the reason behind it? Just mark here: ortho nitrophenol, para nitrophenol and meta nitrophenol. OH, this is ortho nitrophenol, NO2, NO minus positive, para nitrophenol, meta nitrophenol next, meta nitrophenol, then para nitrophenol. Okay, so para nitrophenol has higher boiling point than meta, then ortho. The reason is here, the para nitrophenol makes intermolecular hydrogen bonding. Again I repeat, intermolecular hydrogen bonding, while the ortho nitrophenol forms intramolecular hydrogen bonding. Okay, so here is intramolecular, para nitrophenol intermolecular hydrogen bonding means the O minus here again can attach to the another molecule of para nitrophenol through hydrogen bonding. O minus here hydrogen of another phenol, para nitrophenol. Okay, in this way it will form intermolecular hydrogen bonding, and intermolecular hydrogen bonding is stronger than intramolecular hydrogen bonding. That is why para nitrophenol has higher boiling point. Okay, higher boiling point. Next, meta nitrophenol. In meta nitrophenol, some extent there is also intermolecular hydrogen bonding like para nitrophenol, but less than that of para nitrophenol. Okay, so next is ortho nitrophenol. In ortho nitrophenol there is intramolecular hydrogen bonding. Intramolecular hydrogen bonding, how? You can see here, if you draw the structure of this here, okay, ortho nitrophenol, you can see the OH, okay, here is nitro group, N double bond O, N single bond O minus here, and double bond O positive over nitrogen is tetravalence here, positive charge over nitrogen. The O minus oxygen minus coordinate to the hydrogen through hydrogen bonding. This is intramolecular hydrogen bonding, means within molecule. Within molecule the bond is known as intramolecular hydrogen bonding, and intramolecular hydrogen bonding is not stable. Okay, means stable, less stable than intermolecular hydrogen bonding. So that is why the order is para nitrophenol has higher boiling point than meta nitrophenol than ortho nitrophenol. Okay, all of you got it? So next, so number V property or physical properties of phenol, that is IR frequency. IR frequency means infrared frequency. You just have to remember the frequency value. In infrared instrument or IR spectroscopy, you will find the difference frequency value of different bond. There is oxygen OH, okay, so write the value only in frequency. This is frequency in centimeter inverse we measure. So OH bond, OH stretching frequency, write OH bond stretching frequency, value will be around 3200 to 3650 centimeter inverse. Okay, OH stretching frequency, and OH bending frequency, OH bond bending frequency will be 1300 to 1400 centimeter inverse. And there is carbon oxygen single bond, so carbon oxygen stretching frequency will be around 1230 or to 1250 centimeter inverse. These are the value, frequency value. Okay, you have to remember. Okay, so now come to the point number 6 number physical properties of phenol, that is acidic properties. Acidic properties of phenol. The question much often asked from this property, acidic properties of phenol. So alright, under this, phenol is more acidic than aliphatic alcohol, but less acidic than carboxylic acid. What? Carboxylic acid. Okay, just why phenol is acidic first. So if look at the structure of phenol here, this is the structure of phenol. Okay, if phenol will dissociate, what it will form in aqueous solution? If it will dissociate, what it will form? It will form O minus phenoxide ion, that it is known as phenoxide ion, and this is phenol. Okay, so there is a concept, write the concept. The acid is strong, we call the acid strong if the conjugate base is weak and stable. Concept, right? Acid is strong, acid is said to be strong, if the conjugate base of that acid, here the conjugate base is phenoxide ion, phenoxide base is weak means less reactive, weak and stable, it should be stable. So how to know the conjugate base is stable or not? How to know? If the conjugate base, okay, if in the conjugate base there is charge distribution or charge delocalization or resonance takes place, okay, then we can say the conjugate base is stable. And if the conjugate base stable, we can say the corresponding acid is stronger acid. Okay, so phenoxide ion, look, is there any resonance takes place or not, or charge distribution takes place or not? Look at the resonating structure of phenoxide ion here. Okay, this is O minus, this is phenoxide ion. Okay, resonating structure, when the negative charge returns to carbon oxygen single bond to form carbon oxygen double bond, this double bond moves over to this carbon, ortho carbon. Mark the arrow mechanism. This is the fast transition state. Then the C double bond O, and this bond moves over to here, then negative charge here, and there is a double bond here, double bond, double bond. Okay, negative charge here. Okay, and lone pair of electron. So when, and the second step, what will happen in the second step, when the negative charge again returns to this carbon carbon single bond to form carbon carbon double bond, this bond moves over to what, this is para carbon to para carbon. So what is the structure, right? Double bond O, here single bond, and this bond moves over to this carbon, negative charge as negative charge, and lone pair of electron, and here double bond. Okay, in the next step what will happen, next resulting structure, minus ion again return to carbon carbon single bond to form carbon carbon double bond, and this bond moves over to this ortho carbon. Okay, so what is the structure? You can write double bond O, here is a negative charge, double bond, and here double bond. Okay, next after, if this negative charge again returns to carbon carbon single bond to form carbon carbon double bond, and this bond moves over to oxygen O minus, which is similar to the number 1 structure. So it is cyclic manner, it will form again this one. So this is 4 resonating structure. Here is 4 resonating structure. Because of this resonance or charge distribution or charge delocalization, the phenoxide ion is stable. That is why the corresponding acid, that is phenol here, is acidic in nature. Okay, so I am giving you 10 seconds. You can take screenshot in your mobile. Also you can overlook this whole green board. Within 10 seconds I have various things. So after this, just look at here. So now you know why phenol is acidic. Then coming to why it is more acidic than aliphatic alcohol. If you take an aliphatic alcohol, let us suppose R is any hydrocarbon ROH. If it will dissociate, what it will form? RO minus and H plus. Okay, so here the alkoxide ion or RO minus. Here you can find no resonance or no charge distribution or charge delocalization takes place. Okay, so that is why the conjugate base is not stable here. Conjugate base RO minus is not stable here, but it is reactive. You can find this is very reactive. Also it behaves as a nucleophile in organic reaction. So it is not stable and more reactive, not stable, more reactive. And more reactive means not weak, it is strong. That is why ROH is not a what, strong acid, and less acidic than, not a strong acid, and less acidic than phenol. Okay, so second reason you find. So next I have a question for you. Between cyclohexanol and phenol, which is more acidic? This is a task for you. Practice it. Write in the comment section which is more acidic. Write in the comment section. Okay, between cyclohexanol and phenol, which is more acidic? The concept, the fast concept we have to use only. So this is, we studied only phenol is acidic than aliphatic alcohol, and why is phenol is acidic. Next, if suppose to that phenol, if to that phenol there are substituents or groups, means electron donating groups or electron withdrawing groups attached to that phenol ring, then what will be the acidity trend of phenol or those compounds? So right in the fast divides the point here, you can divide in 2 category. In the fast category you can write let us suppose capital I, means to that phenol ring, if suppose there is electron withdrawing group attached to that phenol ring. Okay, so write effect of electron withdrawing group to phenol ring. Okay, so electron withdrawing groups are what? Okay, electron withdrawing groups are those groups which withdraw electron towards itself. So example, for example, electron withdrawing group examples are nitro group NO2, cyanide group. Okay, halogen, for all halogen I am denoting it as X. Okay, halogen and CHO aldehyde and COOH, carboxylic acid. These are the some examples of electron withdrawing groups. If those electron withdrawing groups are attached to the phenol ring, then what will be the acidity trend? Okay, let us suppose take an example, that is para-nitrophenol. Okay, this is para position, para to OH, this is para-nitrophenol. So the question is, if para-nitrophenol is more acidic than that of phenol or not. How to know? If para-nitrophenol dissociates, what it will form? It will form O minus, Na2 and H plus. Okay, so same concept, if acid is strong or not. How to know? If the conjugate base is weak and stable. So how to know conjugate base is stable or not? By seeing the resonating structure or charge distribution or delocalization of charges. So draw the resonating structure of para-nitro. This is para-nitrophenoxide ion. So draw the resonating structure. This is important and it may ask in your examination too. O minus, draw it here, O minus and Na2, N double bond O minus, nitrogen tetravalence positive. Okay, throw in similar resonating structure. Okay, this bond moves over to this carbon, ortho carbon. What is the next product? Double bond O, negative charge, double bond O, and here nitrogen, oxygen, positive, negative. Okay, in the next point what will happen? The negative charge returns cyclic manner. This bond moves over to this para carbon. Okay, so this double bond, here is negative charge now attached to nitrogen, positive, double bond O, oxygen, negative. In the next step what will happen? You can here then also double bond. The negative charge here, okay, here nitrogen electron means more electron deficiency. First of all, nitrogen is electronegative element, again positive charge over electronegative element makes it more electron deficiency. So the negative charge, instead of moving this way, it will resonating participate with the nitro group. While it donates electron to the antibonding of nitrogen, this double bond moves over to oxygen. Okay, what it will form? Double bond O, double bond. Here is double bond O, nitrogen, oxygen minus, here is positive charge. Okay, so in the next step what will happen? Again, next resonating structure, oxygen O minus returns, this bond moves over to carbon single bond and this bond moves over to this ortho carbon. Okay, just mark the arrow mechanism and by practice you can understand only. The minus, here double bond, nitrogen, positive charge, double bond O, here is O minus this side and the other side is double bond O. Okay, so in the next step the oxygen O minus, the negative minus charge returns to this carbon single bond to form carbon double bond. This bond moves over to oxygen, and this step, after this step the product which is formed similar to the product number starting product. Okay, so that is why there is 5 number of resonating structure. How many number of resonating structure? 5 resonating structure. But in case of phenol, there is how many resonating structure? 4 resonating structure. Though one more extra resonating structure is because of the presence of nitro group here. Okay, according to the concept, more the resonating structure, more will be the acidity. What? More resonating structure, more will be the directly proportional, more will be the acidity. So that is why para-nitrophenol is more acidic than phenol. Okay, and also the presence of any of the electron withdrawing group to the phenol ring increases the acidity. Okay, if suppose instead of NO2 here cyanide or halogen or CHO or COOH groups are attached to this phenol ring at this para position or any position, it increases the acidity, okay, even more than that of phenol. Okay, so okay, look at this side. Let us take a question from entrance corner. Okay, the question is write the acidity order. Write the acidity order among ortho nitrophenol, para nitrophenol and meta nitrophenol. Ortho, para, in short I am writing meta nitrophenol, nitrophenol, ortho nitrophenol, para nitrophenol and meta nitrophenol and also phenol. Compare all four. Acidity order of these four. I am writing the acidity train. The answer is para nitrophenol is more acidic than ortho nitrophenol, and ortho nitrophenol is more acidic than meta nitrophenol. Okay, and meta nitrophenol is more acidic than normal phenol. Okay, anyone guess the train, how this trains come? Okay, so now write the italic point number 2. Okay, in italic point 1 we studied the effect of electron withdrawing group to phenol ring, and in point 2 write effect of electron donating group, EDG, electron donating, effect of electron donating group or electron releasing group to phenol ring, means how the electron donating substituents when get attached to the phenol ring, how it affects the acidity of phenol. So write in point 1 the presence of electron releasing or electron donating group, the presence of electron donating groups, okay, groups decreases the acidity, decreases the acidity of the aromatic ring, here phenol, aromatic ring overall means presence of these electron donating groups decreases the acidity of the aromatic ring overall. What are the electron donating groups examples? Electron donating group examples are amine group NH2, hydroxy group OH, CS3 methyl group and OCS3 methoxy group. These are the examples of electron donating groups. Okay, that is why what is the region next? Region. Okay, write the region. I will explain the region. It strengthens what? The presence of electron donating groups. The electron, write electron donating groups. Electron donating groups, EDG, electron donating groups strengthens the negative charge, strengthens your negative charge over phenoxide oxygen and inhibits charge distribution or resonance process. Charge distribution inhibits charge distribution so that it destabilizes the conjugate base results in weaker acid. Okay, what is the reason? Says the electron donating groups strengthen the negative charge over the phenoxide oxygen. Okay, that is the conjugate base phenoxide oxygen, and inhibits charge distribution. It inhibits the charge distribution after that or resonance process, so that the it destabilizes the conjugate base. Conjugate base will be destabilized. There is no resonance, then there will be conjugate base will be destabilized, in the result in the weaker acid. So by taking example we can understand this. So for example, write paracresol, CRESOL. Paracresol is weaker acid than phenol. Okay, so paracresol, what is the structure of paracresol then? So this is phenol and in para position there is CH3 group attached. This is known as what? Paracresol, P-cresol. So it is less acidic than phenol. Why reason? This is CH3 group is a electron donating group, and if it will dissociate, what it will form? The conjugate base will be O minus S plus here plus H plus H plus. Okay, sorry. So here is CH3, and those CH3 is a electron donating group. It donates its electron through the aromatic ring to the oxygen, and it strengthens the negative charge. CH3 is electron donating group, and it strengthens the negative charge over this is phenoxide ion, and destabilize and inhibits the process of delocalization or resonance, so that the conjugate base here become unstable, okay, or least stable. As the conjugate base is unstable here, then the corresponding acid here is paracresol we are taking. So paracresol is less acidic in nature, okay, less acidic in nature, less acidic than phenol. If instead of CH3, if other groups like NH2OH and OCH3 groups also there, those whole compound become less acidic than that of phenol. Okay, let us take an example. Okay, in example, compare the acidity of two compound, that is 2,4,6 trimethyl 2,4,6 trimethyl phenol and 2,4,6 trinitrophenol. Okay, which is more acidic? The structure of these two are, I am writing phenol 2,4,6, this is 2 position, this is 4 position, this is 6 position phenol. Okay, trimethyl 3-methyl group to 2,4,6 CH3 and here is similar structure 2,4,6 trinitrophenol. Which is more acidic? Okay, which is more acidic? So how to know? There are 3 NO2 groups, electron withdrawing groups. So electron withdrawing groups increases the acidity of phenol ring. So that is why 2,4,6 trinitrophenol is more acidic than 2,4,6 trimethylphenol, and the methyl groups are electron donating group, decreases the acidity of the ring. And if you compare the pK value of these two compounds, here the pK of 2,4,6 trimethylphenol is around exactly 10.9 and pK value of 2,4,6 trinitrophenol is 0.4. Okay, all of you know the pK values. So I have a question for you. Question, write in the comment section how pKa and Ka, okay, how pK and Ka related to acidity of compounds. Okay, what is the relation between the pK and Ka value with the acidity of any compounds? Okay, write in the comment section. This is a question for you. So at last, take an example from entrance corner. So write the question. Write the order of acidity. Write the order of acidity among, I am giving you 5 compounds. You have to write the acidity order. First is para-nitrophenol. Second is para-chlorophenol. Third one is third is normal phenol. Fourth one is para-methoxyphenol, and fifth one is para-methylphenol. Okay, so these are the 5 compounds. You have to write the acidity trend or acidity order. Okay, so para-nitrophenol, para-chlorophenol, phenol, para-methoxyphenol, para-methylphenol. Okay, so you have to write the acidity order. I am giving you the hint and write also the answer. You have to practice and say me the region in the comment section. So para-nitrophenol is greater acidic than para-chlorophenol, greater than phenol, greater than para-methoxyphenol, greater than para-methylphenol. Okay, so this is, you have to give me the region. Give region in the comment section what is the reason of this trend. Okay, so for today that's all. See you in the next class. Stay happy, stay healthy.